Good afternoon. I know it's the last talk of the day. I'd really appreciate everybody being here, and thank you for making this trip to Inforce. My name is Peter O'Donnell. I'm a Principal Solutions Architect here at Amazon Web Services. Thursday marks 8 years for me, working directly with our customers to help them be well architected on the cloud. I've had the privilege of working with some of our largest and most challenging customers, and I've had the opportunity to lean into cryptography here at AWS. Cryptography, as of course you understand, is the root of trust for a lot of customers coming to the cloud. That they believe they can be secure on the cloud, not only because of all the other security solutions and capabilities that the cloud offers, but also because, I'm sorry, I'm projecting the whole room, I can stop doing that, can't I? But also because we offer world-class encryption. And that encryption is the same that you can receive not only for the proverbial kid in the dorm room, but also if you're a major enterprise. And like everything we do here at AWS, it's built to an enormous standard of rigorous, obsessive ownership in our security. And so when we think about the future of cryptography, there's actually kind of a weird thing that either is or could be on the horizon. And that's this idea of what the world would be like, on a cryptographic basis anyway, if it is possible that a sufficiently powerful quantum computer comes into being. I'm going to talk about Crypto 101 real quick, give you a sense for why this is a challenge. Then we'll talk about a long-term view. Here at Amazon, we are long-term thinkers and long-term owners with the intention to build a business that will outlive us. We make very deliberate long-term investments. And what we've done with post-quantum cryptography is exactly that. So let's talk about a security lifetime. When you design a crypto system, it not only needs to work for the period of its deployment, but the ciphertext it produces, the protected data that it yields, itself has some kind of lifespan. And when you design a crypto system, it must be long enough for both. It must be usable, and it must produce ciphered output that can be durable for the long term. And when I say durable, I really mean resistant to compromise. All of cryptography is fundamentally predicated on this idea of very hard problems. And if the problem is hard enough, there's not a simple magic way to solve it without the key. And that's how you secure your data. And when we think about the duration for security with cryptographic systems, we expect that the algorithms that we use are well understood. And this takes a long time. Again, this idea of cryptography being based on the necessity of hard problems, such that there's not a simple way to cheat the system, that the only way to really get at the protected data is to have the key, and that there's not secretly some kind of other toehold for an adversary, whether a casual one or a determined, highly funded, potentially nation-state adversary, to attack the crypto system. And so when we think about this, we want crypto systems that can only be done the hard way. That there's not secretly, again, some kind of, oh, I discovered a flaw, and now I can recover the protected data. I can recover the plain text data. And so when we think about how can you be sure that there's not going to be a secret, unknown flaw in the crypto system, this requires a long period of time. The gold standard for bulk encryption or encryption at rest is the advanced encryption standard. This replaced something you may remember called DES, the data encryption standard, and AES has been around for a long time. It was first introduced and went through an enormous period of academic scrutiny, of an examination of the crypto system. In fact, it is well understood that you cannot have a trustworthy, reliable crypto system where the system itself is a secret. The system must be well understood for exactly this reason, that it's the only way to ensure that it's integrity, that it has integrity, and that it's, again, not subject to some kind of unknown current or future method of compromise. So it takes a long time, literally millions of person hours to determine this. And then once everybody kind of feels good that, okay, this software, this magic formula, that if we take the data, we take a key, and then we do a bunch of goofball stuff to it, out the back comes ciphered data, and that the only way to recover that ciphered data is by an authorized person in possession of the key. So it takes a long time to develop that system in the first place, and then takes another really long time for everybody to wire it into their standards. In the beginning of AES, in the beginning of a lot of cryptography, it was very expensive computationally. I'm old enough to remember installing SSL accelerator cards in web servers that had to handle high scale, high volume cryptography. Because if you put that work on the CPU, it would bury the general purpose CPU. So you had to have dedicated special hardware. Well, today, the regular main brain, the CPUs in mainstream computer systems, whether from x86 or ARM and everything in between, has dedicated support for this hardware to perform these encryptions, perform these cryptographic operations in a way that is fast and low latency and totally easy to do. So not only, again, do we have the long period to develop the algorithm in the first place and be sure it looks right and be sure that it's not like secretly with a crack in the wall, it then takes another really long period of time for the industry to actually adopt it and make that cryptography easy to use and ubiquitous in its availability, ubiquitous in its performance, and ubiquitous in its ability to be consumed by software built atop of it. So because of this long-term journey, when we think about long-term confidentiality, there is a problem on the horizon. Today, when a client interacts with the service, that network traffic itself can be encrypted, TLS, God bless. We recently went to TLS 1.2 as a minimum standard across the board at AWS, and we also recently launched TLS 1.3 support for all AWS APIs, which is terrific. And there's different crypto suites available within those different protocols, but this idea being that they're pretty good, like it's safe, they're well understood. But going back to this idea of long-term confidentiality, that if a sophisticated adversary is capable of capturing this ciphered traffic, what if there's a weakness on the horizon? And as it turns out, while it's not a sure thing, there are new capabilities coming in the form of a sufficiently powerful quantum computer. There are ways to attack and undermine those crypto systems that today are already well understood. These algorithms have existed for decades, but they're infeasible to operate. They're infeasible to actually perform on a classical binary computer system. But there is a new capability possibly coming where these algorithms that again are well known become fast and become feasible, and that the hard problems that classical asymmetric cryptography is based on stop being hard problems. And if they stop being hard problems, then the crypto system has been weakened and in some cases undermined entirely. So let's pause there and pivot to this idea of long-term roots of trust. What does it mean to protect data for a period of time? What kind of data needs any kind of understood horizon for how long it ought to be protected? When we think about the difference between a 1-year view and a 15-year view, we can also correspondingly think about the necessary strength of the crypto system used to protect that data. And that if it's a 1-year piece of data, and it could be compromised by working hard to recover the key, and it takes 2 years of work, well, maybe it doesn't matter. And you could imagine something like an earnings report that needs to be secret for a time, right until you make it public. So again, there is a new capability. Now that we've kind of understood this idea of strength, the ways to undermine it, and how long it takes to build a new type of crypto system, let's talk about this new kind of capability. A classical computer system has bits, 1 or 0, on or off. It is the foundational basis for everything that you consider to be a computer. And as if you're computer science nerds, as I assume you are if you're here today, it's a foundational thing. And higher order APIs depend on lower order APIs that depend on lower order machine instructions that depend on lower order constructs. And the lowest order construct in a classical computing is simply the binary system. But there's a new type of computer, this idea of a quantum computer. And instead of a 1 or a 0, there's this new type of thing called a superposition. The superposition can lend itself to a new type of bit, this idea of a quantum bit or a qubit. In the same way that we've understood the evolution of classical computers to go from simple 8-bit systems to the breakthrough of 32-bit computing with the 386, if you're old enough, that's how old I am, to modern 64-bit computers. Without becoming a supercomputer nerd, you understand that the increase in bits available for the computational operation maps directly to the power and the capability of the computer. And today, quantum computers exist, but they can only use very few qubits at a time. But it's possible that that will not always be true. And it's possible that quantum computer systems will develop the ability over time, potentially tens of years, in a far distant future or not, of a sufficiently powerful quantum computer. And so that brings us back to these algorithms. We know that these algorithms, were they able to be performed on a sufficiently powerful quantum computer, undermine the basis of a lot of the hard problems that form the soul of traditional asymmetric cryptography. And so we know that if we can feed these algorithms to a sufficiently powerful quantum computer, a lot of things change. Now the good news is with symmetric, the reduction in security is basically to have the bit depth of the key. Because you still kind of have to do it the hard way. You just get a head start. So instead of trying every possible 256-bit key, which is like a weird dumb number like molecules in the universe kind of thing, it's now a 128-bit key, which is still, I assure you, a weird dumb number. But what it does to asymmetric is quite different. And so as we think about the future timeline for data that needs to be protected for the long term, there is something coming, maybe. And if this kind of computer comes into existence, we must begin now, really years ago, and don't worry, we did, we're getting to that part, to develop it. Because as described earlier, it takes a long time to develop a new algorithm, and then it takes another long period of time to adopt that new kind of crypto system. And so if you're protecting temporary credentials, or as I mentioned earlier, earnings reports, or even credit card numbers, the period of validity and the period of sensitivity for the data that you protect is necessarily pretty narrow. Even a credit card is still only going to be valid for a period of years. And earnings reports maybe only need to be secure and sensitive for a period of weeks or months. But when we get to longer horizons for how long the data must be secure, we are running into the timeline and horizon of the potential for a sufficiently powerful quantum computer to come into existence. And again, because of the time it takes to develop these algorithms, because of the time it takes to then adopt and make these algorithms universally available, we must begin today. And again, good news is we actually started several years ago. So this is relevant to you. If you're working with AWS, you maybe have bet your business on our capabilities. We love that for you. We obsess over helping you get it right. We obsess over helping you stay secure. And if you're building your business on us, very likely you intend that business to last a long time. Dozens, tens, maybe longer of years. So with our stated commitment of security being our top priority, we have to worry about this. Again, it remains possible that the sufficiently powerful quantum computer never comes into existence. But it might. And if it does, we're going to have some really hard problems to solve tens of years from now. And we generally think that this is serious. And with regard, if we think this is serious, you should probably think this is serious too. But the good news is, we're working to help you, and so is the industry at large. So what is the industry doing? Well, as it turns out, when I say we need to begin today, we actually began years ago. I'm talking about this today, and I get to say the word we a lot, but a lot of people who are much smarter than I am, actual cryptographers, and you're going to hear from one in a minute, have been working on this for a very long period of time. And so it was a decade ago that the industry really started chugging on this problem. And the American National Institute for Standards and Technology has been doing a bake-off. I mentioned earlier that it can take a decade, millions of person hours to validate that the new solutions aren't suddenly wobbly. That these new capabilities, call them quantum safe or quantum resistant cryptography, don't actually have very simple, serious flaws. And that work has been going on for a long time now. And so NIST started with maybe a dozen of these algorithms, and we submitted a couple of them. They've baked off and reduced them now. And some of them that look good were actually found to be very crackable. And again, that's why it's so complicated, because it takes the academic community, the cryptographical community, a long time to prove this out. And so going back 7 years ago, NIST put together a real serious plan to get there. And we expect in just next year to publish new formal standards for what post-quantum cryptography ought to look like. This is that 10 years I mentioned earlier. This is that millions of person hours necessary to make sure that these algorithms are not wobbly, that they're not secretly flawed in unacceptable ways. So to talk further about what it is that we are doing to get into the real math, and again, I'm a solutions architect. I get to say we when I talk about the Nitro system, but I want you to hear from a real cryptographer. Matt Campagna has been with Amazon Web Services for just about a decade, one of our chief cryptographers, and is very close to the NIST standards body and has been professionally and personally working on post-quantum algorithms and post-quantum engineering that entire time. And so without further ado, I'd like to introduce my friend, Matt Campagna.
Thanks, Peter. Thank you. So, as Peter indicated, there's this threat of a quantum computer is going to impact or is capable of solving some well-known hard math problems that we use today. In particular, the integer factorization problem, the discrete log problem for finite field or elliptic curve cryptography. The good news is there's just plenty of super hard math problems. And so we've been working on, and some of those super hard math problems that can't be efficiently solved on a quantum computer are suitable for turning into asymmetric cryptographic schemes. And these are the hard problems that the most recent submissions to the NIST process were focused on. And NIST and the international community of cryptographers have been focused on the submissions on things like the shortest vector problem in a lattice or lattice-based cryptography, the syndrome decoding problem, which is sort of coding-based crypto systems, and a variety of other schemes that were proposed as potential underlying math problems to build a cryptographic system. So what did NIST select? At the end of the process, NIST selected one key encapsulation mechanism, a chem, for standardization called Kyber. And that's based on a lattice-based system. And they have a few, they're going to standardize a few additional chems. One called, either Bike, HQC, or McLeese. I won't get into the details of those. And they selected 3 signature schemes to replace the signature schemes we're using today, in particular dilithium, Sphinx, and Falcon. So their preferred schemes are the lattice-based schemes, Kyber and dilithium, for key encapsulation or key agreement, and digital signatures. The lattice-based crypto systems have been around for a long time, 30 years. They've been analyzed since the late 90s with Entru. And NIST is going to standardize these, hopefully, during 2024 in what's called the Federal Information Processing Standard, which is required for sort of US government protection of information. So we expect to see that first draft today, sometime this summer. So a little more about Kyber. So this slide depicts down the column some of the cryptographic schemes we use today compared to Kyber at different security levels. So as a minimum, we try to deliver 128-bit security, and we're recommended security level today is 192 bits. So that compares to the elliptic curve on a prime curve of 256 or RSA 3072, and that compares to the scheme called Kyber 512. And the next 2 columns are the public key size and the ciphertext size. And that's essentially what you have to exchange when you want to negotiate a key. One person will send the public key, and the other participant will respond with the ciphertext. And you can see Kyber is adding roughly 750 bytes over elliptic curve to that transaction in each direction, or over roughly 400 bytes compared to RSA 3072. And the next 3 columns are the microseconds required to execute the 3 fundamental functions that you have to do to perform the key encapsulation mechanism. There's key generation, which you're generating a brand new key. There's encapsulation, which is like encryption. And then there's decapsulation, which is similar to decryption. And the first thing that really stands out here is the amount of cycles it takes to do an RSA key generation. And it's one of the reasons why we don't typically use RSA for sort of ephemeral key establishment. It just, the primality testing required is too computational intensive. But the key generation in terms of microseconds, 1/1,000,000th of a second between Kyber and elliptic curve, 20 microseconds you're really not going to notice on a processor. And all these performance numbers were run using our AWS libcrypto library, where we've implemented Kyber and a number of other post-quantum algorithms. And then when you get to the encapsulation and decapsulation, you can see that Kyber 512 really outperforms both RSA and elliptic curve in terms of performance. So among the submissions to NIST, Kyber was one of the highest performing algorithms. And you can see it's faster than elliptic curve. And this is comparing elliptic curve assembly code to regular C reference implementation of Kyber. For signature schemes, I have the schemes we commonly use today, ECDSA on a prime 256 curve, RSA 3072, dilithium 2, Falcon 512, and a variant of Sphinx, all at the 128-bit security level. And here you can see, what you really need to do to exchange a valid signature is the recipient has to have the public key and the signature. You can see there's quite a bit of difference between the different schemes, where ECDSA is very small, very compact, 33-byte public key, 64-byte signature at a minimum, and that compares pretty well to RSA, which is about 380 bytes in both directions. Excuse me. And dilithium is in the middle of the pack, really, among all the signature schemes. It adds about 1,000 bytes compared to RSA for the public key and about 2,000 bytes for the signature. So there are going to be applications, especially bandwidth-constrained applications, where the application of these new signature schemes are not going to be straightforward. There's going to be more engineering involved in sort of stretching your protocols or extending your sessions. So with the announcement of NIST selection, there's been an increased number of announcements both within the US government and other governments around the world on their PQ migration plan. Most notably is probably the National Security Memorandum on mitigating risks due to quantum computing. That was followed up by a Office of Management and Bureau memo for migrating to post-quantum cryptography. And that mandated that government agencies that have high-value assets in their system have to begin the inventorying of their public key algorithms within their systems. And that report was due back to the Office of Management Budget this past May. And that was followed up with some legislation, the Quantum Computing Cybersecurity Preparedness Act, that required all other government agencies to do the same within the following year. So that would be next May. A little ironically, May 4th. I don't know if there's a joke involved in there or not. But we see similar transition plans happening. There's the BSI in Germany, which published their QS Quantum Safe Crypto Fundamentals and Recommendations. There's the ANSI in France, which has QSC Fundamentals and, their Post-Quantum Cryptography Transition Plan. Similarly, Canada and Australia have published their migration strategies. One of the, probably leaning in on that page that I didn't dive into is NSA's Commercial National Security Algorithm Suite 2.0. And they're probably a little more definitive on what they expect to be provided when it comes to procuring equipment for national government, national security needs. So you can see their expectation is for software and firmware signing that companies are already, their new products and services that require that are already have an option for either using or testing post-quantum cryptography. There's a stateful hash-based signature scheme that was standardized about 3 years ago, and that's what their expectation is. There will be early adoption of that today, with it being available by default in new services and features for software and firmware signing by 2025. So that's not a lot of time. And then they expect that end date of 2030, that will be the only option. All software and firmware signing for products will only have post-quantum signature schemes. You can see the next line down is this web browser and cloud services. And the expectation there is that by 2024, sometime in 2024, these new post-quantum algorithms, the Kyber, will be available for web browsing traffic and cloud security traffic. And then having that on by default as soon as 2025. So what does that mean for AWS? Well, the area that we're most focused on is the long-term security of our customers' data. And the place we're most concerned about is when that data is being communicated to us over open networks, like the internet, or even a direct connect lease line. Good news is most of those connections, all of them that I know of at least, are using publicly defined standards from the Internet Engineering Task Force. So these are protocols like TLS, SFTP, Secure File Transfer, SSH. Our customers are using SSH to connect to their EC2 instances, and IPsec in Direct Connect. So we're in the process of evaluating all those connections, developing the necessary standards to do post-quantum, and testing them in our infrastructure today. And I'll go into that in more detail. From there, we have to secure all our internal networking. Good news is most of those also are based on these open standards in the community. From there, we're going to work on our cryptographic services. So we have a number of services: AWS Key Management Service, Cloud HSM, Secrets Manager, and our Certificate Manager. And we have to both secure those against a quantum adversary, but also have those services updated so they can deliver post-quantum solutions to our customers and our internal services. Once that work is done, all our other services, by and large, depend on those public network protocols that we're upgrading, as well as our internal cryptographic services to secure the data. So most of the heavy lifting will be done at that point. So we've been working in four primary areas of innovation over the last 10 years, starting with the Institute for Quantum Computing and the NIST, the ETSI, European Telecommunications Standards Institute, to sort of bring together both academic, governments, and industry to focus on this long-term goal of quickly developing new cryptographic algorithms. And NIST really was the entity that really answered that call. They were part of that workshop. They started the NIST PQC standardization process. NIST is one of the few global organizations that can really command the attention of the international cryptographic community to focus on a handful of algorithms to get to that million-person hours of research and evaluation of these algorithms. We continue to participate in ETSI Quantum Safe Crypto, where other core primitives are being defined, like how to do hybrid key establishment. And then we're doing basic research, along with the submissions that were done to NIST, when we have team members that are on a variety of these, including Kyber, dilithium, Sphinx, and Bike. We're producing the literature around that. So you can't just write a standard that has interoperability. You need to have a rich literature base of which that security, the overall security of those algorithms, are based on. So other professional cryptographers can analyze that, dispute that, augment that, etc. So those are the areas in the core primitive space that we've been contributing to. After that, we've been focused on the protocols, that outer shell, how our customers are going to connect to us over open networks. We've been leading the work on PQ-TLS, starting with 1.2. Now we're focused on PQ-TLS 1.3, as well as SSH, Secure Shell Protocol, which is widely used, not just to connect from one host to another, but also in the administration of a lot of network equipment is using SSH under the hood, as well as a variety of other protocols that we see essential to our customers. And we're not just building those protocols or defining those protocols, we're building the libraries to implement them, and we're testing them today. They're in our continuous deployment pipelines. They've been there since 2019. We've been deploying S2N TLS with PQ, and that's available today. The PQ TLS is deployed everywhere S2N is, but it's turned on our most sensitive cryptographic services, in particular KMS, Secrets Manager, and ACM. And then today you can use our AWS SDK for Java 2.0 to connect to that TLS endpoint. And just this week we announced PQ Secure File Transfer for our AWS transfer service. So I'll go to that in a little more detail in the following slides. And then we're also working in some collaborations. So we're participating in the National Cybersecurity Center of Excellence, where we're running some of these experiments to ensure that people aren't just generating specifications, but they're generating interoperable implementations at the same time. So we don't have to wait for the algorithms to be done standardization. We can also start the integration of these algorithms into the protocols at the same time. And that's what we've been doing for the last 5 years, keeping those 4 years, keeping that implementation aligned to the development of the proposed standards. So I've said hybrid public key, post-quantum hybrid key exchange a few times. I'll go into a little more detail explaining how a CHEM works. So down on the bottom half of this is the post-quantum scheme, which is a key encapsulation mechanism. And you can think of it a lot like a safe, where the secret key is just a combination to the safe, and the public key you can think of is the safe just being left wide open. And the elliptic curve is depicted by these cans of paint. I start with a stock base color paint, G, that everybody can get, and I'm going to mix in a private color that I'm not sharing with anybody else. And that'll give me a new color. And Alice is going to send this new color paint and this open safe over to Bob. Bob is going to start the key encapsulation mechanism, and that'll generate a shared secret. So now Bob has this shared secret that he somehow has to get to Alice. He will also take that same base can of paint and mix in it his private color K. To get another color paint, he's going to seal that safe up and send both that can of paint and the safe back to Alice. Now Alice knows the secret combination. She can open the safe and extract the same shared secret. By analogy, similar analogy, both of them will mix in their private color paint into their prospective exchange cans of paint and arrive, if you mix 2 or 3 colors, inevitably you get brown. And now Alice and Bob have 2 secrets. This hidden can of paint, DKG, and this shared secret that was sent in the safe. And they can use that. They really derive a key from those 2 secrets. And then they can encrypt their session data. And then any onlooker, Eve, that's watching this transaction go by, has access to that base color can of paint, the exchange can of paint, and the public key and the ciphertext, doesn't learn anything about the secrets. And further, if an adversary can break one of the schemes, let's say we deploy a post-quantum scheme early and it's not secure, well, that doesn't help them break this communication channel because they'd have to break both of these schemes. And being able to have something like PQ hybrid means that we can begin integrating and testing these NIST submissions early and figuring out which ones are going to work well in our infrastructure today. And learn, like, do we need to change our protocols, or will the protocols be acceptable in terms of performance? So I think they are. This slide depicts the performance of integrating Kyber with EC Diffie-Hellman in our TLS 1.3 in S2N. And so down the column you have both the classical scheme and the hybrid scheme, EC Diffie-Hellman with Kyber 512. And you can see from the bandwidth, this is the bandwidth of the handshake for a TLS session. So using a classical scheme, it's about 3,500 bytes, and using this hybrid scheme, it's 5,900 bytes. So you're adding in, roughly 2,500 bytes to this communication channel. So a non-significant increase in the number of bytes. But the performance is quite minuscule. It's 0.3 milliseconds on average for that handshake. And that includes, the transmission of those bytes, the various copying and pasting above different buffers, and doing all the computation. So it's quite adequate for almost, when you amortize that 0.3 milliseconds over the entire TLS session, which includes whatever you're planning to get or fetch or post, it's quite small and acceptable for use. And we've had this in Key Management Service, Secrets Manager, and the Certificate Manager. And you can use it today. And if you want help learning how to use it, we have a session tomorrow, a workshop tomorrow, DAP301 on PQC with AWS KMS endpoints, SDKs, and libraries. And that'll be here in ACC tomorrow, level 2. So if you want to learn more and how to set it up and how to play with it, I encourage you to attend that session. The other thing we announced just this week is post-quantum algorithm support in AWS Transfer Service. So the AWS Transfer Service is a convenient way for customers to import and export files into Amazon S3 or our Elastic File System. Using regular available file transfer tools like SFTP, which is FTP over SSH, FTPS, which is FTP over TLS, or regular FTP transactions. So what we announced just this week is support for SFTP using post-quantum algorithms. And that started with a draft in the IETF for SSH. And in particular, this draft we published earlier this year introduced 4 new hybrid key establishment methods that consists of different security levels. At the 128-bit security level, at the 192-bit security level, and at the 256-bit security level. So you can go into the console today, go to your AWS transfer SFTP endpoint and configure this PQ SSH policy. You can see it here highlighted on the left, on the orange side, and on the left side in the red box, highlighting the security policy, and using some open source or some widely available SSH tools, including the Open Quantum Safe Open SSH tool or Wolf SSH. You can run this command line, and this is in verbose mode, so you can see printed out in the slide the key agreement scheme that was selected. In this case, it was NIST P384 Kyber 768. And this was all part, some of this work came out of interoperability testing that we did in the national, the NIST Cybersecurity Center of Excellence PQ migration effort. So again, this is available today. You can go and test this. We published a blog earlier today on this. Here's the latest user guide. You can go and it'll walk you through how to configure this for your AWS transfer service. So what can you do? All this work starts with inventorying your cryptographic systems, understanding where you're using public key algorithms, understanding the effect it has on downstream keys, where it fits into your cryptographic engineering. For the standardized cases, investigate whether there's new work being done on PQ standards in those spaces. If you're procuring open source software or buying software or writing your own software, are they working on and testing the PQ alternatives for how to integrate that into your engineering? We all have bespoke engineering in our infrastructure. Those require migration as well. It starts with an investigation. And I really encourage people to begin integrating and designing this into their deployments. So you know early. You don't want to find out later that for one reason or another, whether it's performance or bandwidth, that you're going to need to re-architect your system. That's a very expensive thing. So understanding early if these algorithms are going to drop in and work for your current architecture is essential. So in summary, our goal is to make the PQ transition as seamlessly and easy as possible within AWS. So we're going to migrate our infrastructure, migrate our tooling, because post-quantum crypto is coming to the cloud. And I don't think AWS is not going to be alone in this space. I think we're going to see most of the industry move towards post-quantum security as the default standard over the next 5 years. So we're leading many of the initiatives because we want to lean in and innovate on behalf of our customers and make sure this is as seamless as possible for you. So you can track our development, our latest news. We have a post-quantum landing page down at the bottom. That's where we post all our recent activities. Go there often because that's what we're using to keep our customers up to date. So if you have any questions, you can always reach out to me or Peter. I put his LinkedIn there. We're avid LinkedIn users. Please let us know if you have any questions. If you find you have a migration path that's not accounted for in our strategy, let us know. Really appreciate it. I also really appreciate the time to be able to speak to you. It's a great opportunity to meet customers. It's been a while since we've really I've been to Inforce, so I really appreciate it. And finally, I just want to remind you to complete the survey because we value your opinion, and we respond to those surveys with content here. So thank you very much. Thanks.